I thought about that too.
I gotta wait.
Oh, magnets.
Ooh.
This is where the fun begins. Calm down. Wait, Jacob, what happened?
Lemming problem.
Yeah, proton on the top.
It's kind of funny.
Okay, so let's say that you have a radioactive source that's producing three potential things that you can get out of radioactive decay. You get an alpha particle, you can get an electron, and you can get a gamma ray. So the question being, which one is which? And you're shooting it through a magnetic field. That's what your X's are. So you're shooting it through a magnetic field. Deacon,
The top line is going to be the alpha particle, the bottom line is
why?
because we use the right angle since the alpha particle is a positive.
Okay? So, if the alpha particle coming out like this, hand goes in, force goes up, here's your alpha particle.
Big mass, so it's gonna take a wider radius.
Oh! So, that's another key thing. What do you know about alpha particles compared to an electron? Huge. Much more massive. Okay? So, that's the other reason. There's two reasons why I drew it like that. Number one, it's positively charged. The force is going to direct it up like that. Number two, it's much more massive, so it's going to have a much bigger radius. So the bottom one's going to be your electron, because that's the force that it's going to feel. So if you use the left-hand rule, right, electrons coming out, boom, you got that. Also, that has a much smaller radius. Why?
Much smaller mass.
Much smaller mass, okay? And the gamma ray is the only one that's just going to go straight through, okay? So, because it's just a very, like, basically it's a photon on steroids, okay? So, no, it is. So if you ever hear that, oh, hey, there was a gamma ray burst and it's headed towards the Earth, that's not going to end well. Because gamma rays actually, we call them rays, but in reality they're just, it's like X-rays. X-rays are just very high energy photons. Gamma rays are just exceptionally high energy photons. Enough so that, like, if it passes through your body, that it will, like, jostle around your DNA. And so that's what they think, that might have been like a contributing factor when you get into evolution. It's like, well, how did DNA change? Might have been a gamma ray burst that came through. It basically caused the mutation by altering the structure of the DNA. And so it's like, oh, we're mutants caused by gamma ray bursts. Cool, okay. So here's what, in terms of what you need to know for the test on Monday. So you need to know alpha decay, okay, and that's the easy one because an alpha particle is just what?
Helium.
Yeah, it's just helium.
Without the electrons though, right? Yeah.
Yep, and it's positively charged. So this one's simple. This is the simplest one because you just make the math work out. So you could have, I don't know, uranium 240, I think that's like 92, whatever that is. So this is going to be your parent nuclei. It's so nice to write with a pen that writes, like I don't have to stop it. It's sketchy. Okay? Yes, this is my brand new social scroll. Thank you very much. Christmas came early.
Does that
So
make
then-
bots Santa?
Huh?
Does that make bots Santa?
Yeah, it does. And so whatever that's going to be 90, and that's going to be 236. So basically, make your mass numbers add up to whatever on the parent is, and then make your atomic numbers add up to that. Okay, add 4, add 2. That's the simplest as it gets. Now, what takes a little bit more thought is beta minus decay versus beta plus decay. So here's the difference on that one. So if you have beta minus, so here's kind of what occurs most often. Yes, I can write it in a rainbow, thank you very much. Okay, and just because I can. So
It's a rainbow. That works.
Oh, move your face.
Faster to make it bigger. As if you're trying to erase a large. But when you really mess up a full equation, you go back and use D equals BG where you weren't supposed to. How did that allow? It cost me everything.
Looks like one of those things, you know, like solid block things, scratch them off, a little wood piece.
Yeah.
Okay, so one of the great mysteries of the universe is that really we shouldn't be here at all. No, we really shouldn't. I mean, if you look at the odds, we shouldn't be. And here's one of the reasons, is that when you look at the universe beginning from the Big Bang, which really there wasn't any noise, but we call it that, and there was just pure energy, and you get into hyperinflation, and just the study of what happened, they think, in the initial, like, 1 second after the Big Bang is a whole field of study. And you get energy cooled, you began to get mass out of it from Einstein's equation, E equals mc squared. So if you know how much energy that you have, and you know the speed of light, you can solve for mass. So it's funny how people perceive this equation. The idea that mass can turn into energy, that isn't the problem. Okay, great. You look at like nuclear reaction and explosion, whatever. That's okay. Where it gets weird is if you try and make the door swing the other way. And you take pure energy, however that's defined, and then mass appears out of the energy. Okay? So mass turning into energy, cool. Energy turning back into mass, that gets weird.
Not cool.
Okay? Well, it isn't. And so here's like the classic analogy is that, like, okay, what's the square root of 4? Plus or minus 2. Plus or minus, right? So one of the things that kind of we start still trying to figure out is that when the universe cooled and you began to produce mass, the universe should have produced equal amounts of matter, what we consider to be matter, okay, what we're used to dealing with, and antimatter. So in antimatter, it's identical. Gravity, and they just proved about 3 months ago that gravity even acts the same on antimatter. The only difference is that protons are negatively charged and electrons are positively charged, which is weird in and of itself. But then when they run into each other, they annihilate each other and they turn back into pure energy. So if the universe had produced equal amounts of matter and antimatter in equal quantities, the universe would have been forming this stuff and it would have been running into each other and they would have been annihilating each other right away. Okay? So you could have made matter, but in the end game, it would always just exchange back and forth between matter and antimatter and energy, because the matter would run into the antimatter and they would just annihilate each other, and there we go. So one of the questions is what tilted the scale? What allowed matter to be slightly more prominent than antimatter is? So one of the things they think might be the key is what's known as neutrinos. So neutrinos are these really strange things. They're matter. They are permeating through the universe in very, very large quantities. So it's been estimated, like if you hold up your thumb, about every second, about 50,000 neutrinos go through your thumb every second, okay? And don't sit down and go, oh, I feel it now. That's what that was. No, that's not what that was. Okay? So they're just literally like streaming through the universe. But conveniently, they don't interact. And then neutrinos are their own branch of study because there's like 3 different types of neutrinos, because initially they were missing like 2/3 of the mass of the neutrinos, and it figures out they weren't taking into effect that they travel at different speeds, and that affects the relative mass. It's a whole other section. And so neutrinos are these cool things, but they just don't make any sense. I mean, we know what they are, but they're extremely difficult to study. As a matter of fact, there is a project up in South Dakota, and it was kind of cool because at the time when that was first started, so in Chicago there was something called the Fermi Lab, and the Fermi Lab was like the first particle accelerator in the United States, and it has this like big ring underneath there where they can accelerate particles at extremely high speeds, and they have these big massive magnets that accelerate these particles. And then they would accelerate these particles, and that would have a collision that would kick out these neutrinos. And then in South Dakota, they're building, it's called the Dune, they're building underneath, it used to be a mine, they're building this big, massive, basically detector to try and find out the presence of these neutrinos. So they're shooting them from Chicago and directing them to South Dakota. And so at one point, one of my former students, and they both had the same name, Reed Bowles, was doing a summer internship at Fermi Lab where they were producing the neutrinos. And then I had another former student of mine, Reed Abbott, who went to KU and got a degree in like engineering science. He was working on the detector side of it in South Dakota. So it was cool. So I had one former student that was working on producing the neutrinos, another former student at the same time was working on the other side of it, trying to build the structure to detect it. So it's really tough to detect neutrinos because they don't interact with things very easily. But they think neutrinos might be one of the keys to explaining how the universe got tipped in favor of antimatter versus, or matter versus antimatter. So in terms of what you need to know for the test, beta minus, beta plus, and here's this is how I always remember it, is that beta minus means that you actually add, okay? So in beta minus and beta plus, what stays the same is the mass number, okay? So the total number of what we call nucleons, okay, is the same. You don't change the number of nucleons. What you do alter is the number of protons. So remember, what's the only thing that determines the type of atom an element belongs to? Number of protons. So what they would see is if you had carbon-14, which is radioactive, because the most stable form of carbon is carbon-12. So what they would see is if you had carbon-14 and a sample of that, is that over a period of time, you would see an increase in the percentage of nitrogen. And I was like, oh, the nitrogen wasn't there before. What's happened? So that would be like me, God forbid, teaching a class of freshmen, and then all of a sudden sophomores began to appear in the class. It was like, you weren't here before, how do I explain freshmen turning into sophomores? And this basically we had to figure out. Now, charge has to be balanced as well. So the reason that you kick out an electron out of this process is because of the fact that you're gaining a proton, and then to balance out the charge, then you have to produce an electron so that the overall charge remains the same. So you gain a proton, but you lose an electron. This is the one that happens most often, okay? Now, in beta plus, you subtract from the atomic number. So you start with magnesium, 12, 13. The mass number stays the same at 23. You subtract 1, you get 11. Now to balance it out, this is where the antimatter comes into play, because you're decreasing the positive charge by 1, then to balance that out, then you kick out something that has a positive charge, which is a positively charged electron, otherwise known as a positron. So unfortunately, the positron, as soon as it runs into your normal electron, they just annihilate each other and turn back into energy. Okay, so those are the big things. In terms of calculations, okay, so on this sheet, when you get into something like question number 25, where you have thorium turning into radon and helium, and you want to figure out like the energy that's involved, I will give you all of the numbers, okay? Don't memorize them. I will give you any of those very, very specific numbers for the mass of a proton, mass of an electron, mass of a hydrogen atom, okay? I will give you those. You just have to know how to use them, okay? And what I would recommend, even though what's on your equation sheet, that conversion is 93.1, I would prefer, and I'll put this on the test, that you need to use that 931.49 just because of the fact that you get more precise answers. And why they rounded to 931, I don't have the faintest idea. But it's technically mega electron volts per atomic mass unit. The atomic mass unit cancels out. You get MeVs. Cool, grand, great. Okay, so let me hand out some stuff. Stop that. You got your camera.